So hello everyone, this is Vishal. So we'll start with the seventh week. So okay, so the date has been extended, I guess, till 15th of June for the sixth week, right? Are you able to hear me?
Yes, sir.
Okay. Okay, so I'll share my screen. So, so this session won't be like a big, like this session will go around 1.5 hour or 1 hour. After that, I need to sign up for your quiz marks. So we'll meet again on the Wednesday, I guess. So how many of you have seen the lectures till now? So I don't think so. Okay. Yeah, Ganguly, Trisit Ganguly, you can speak up. Not seen. So most of you have not seen, right?
No, sir.
Okay, it's fine. So I'll just give you the idea regarding the PCA. Okay, so if you're aware, it's fine, but I'll just give you a brief idea regarding the PCA. Why are we doing this? So that because in the lectures, mostly the proofs and all are given. How are we concluding? So I'll just tell you the process, like the PCA, the maths behind that, the basic maths behind that, and what are the result. I'll not tell you how we are getting there. That you can refer the lecture, and that thing we'll discuss on the Wednesday. Okay. So I'll just give you an idea. Like I'll just start with an example. So I just so many of you will be knowing regarding the MNIST dataset, right? So if you have worked on some, I guess earlier, if you have worked on some data set, so MNIST data is the one of the famous data set, I guess. So these are data set where we are having, like for example, it's a data set. You can just, I'll just paste this on your chat box. Also, you can open that and you can go through this blog. It's a really like awesome blog. We'll just get an idea about the PCA, like basic stuff. You'll just get an idea regarding the MNIST dataset also. That will work, I guess, in the next. So these are some of the very like vastly used datasets that we'll go through every time. So there are some music and all going on. So maybe if you're able to,
may you please send this link?
Yeah. Just. So some background music is also coming, or it's fine.
Yes, sir. It is there, but it's like very.
Like I already packed my room. Then also it's coming from outside. I don't know. Like there is some festival or something going on, I guess.
It's not that significant. So.
In fact, it's soothing, sir.
Yeah. So I sent you that link. Okay. So. So this is the MNIST dataset. In this dataset, what happened? The whoever wrote this blog, some Ola, I guess this Christopher Ola, I guess the name of this, the author of this. So we are having this dataset where this, like for example, the handwritten numbers from 0 to 9 was there. Okay, and so we have some big amount of data set like 60K or 70K data set we are having. The training data set I'm talking about. So this type of data set was there, like 5, it's written in the hand, right? 5, 0, 4, 1. So this type of data set we are having 60K data sets. Okay, so 60K means 60K, and then the label of the data set is from 0 to 9, because these are the labels only, like 5, 0, 4, 1 and all. So this data set are like in the visual aspect, right? So visually, so how can we get some aspect from the data set? So there are some work like that. It's not like relevant here, but I'll just tell you how they this, like for example, this is a 5 written, right? So what they did, how they extracted the data from like this 5. So they have changed this, like there's a pixel, right? So you would have heard, if somebody is from electronics, so he'd be knowing about the pixels value and all. So like for example, this converted this 5 into some pixels value, like 28 cross 28. So here it has been done 28 cross 28. So this row has been having 28 pixels, and the column also having 28 pixels. Okay, so for each pixels will be having some value. Like for example, I'll just try to write it here. So for example, if this is written like this, like I'm having a large, like the training data set is very large. So like this, like for example, this is a seed, and here it has been written like 0, it has been written, right? So some sort of D0 has been written like this. So this has been converted into like 28 pixel cross 28 pixel, and each pixel, like for example, I've just made 28 cross 28, and each pixel will be having some value. Like for example, wherever like the pixel generally here, what he has taken, wherever there's a white, he has given 0. Wherever is a black, like for example here, it was, what is that? Yeah, so this pixel, like for example, see, 1 is there. So this has been converted to 28 cross 28 pixel, and see, you can see that wherever there is a very dark black, he has taken 1, right? And wherever there is a bit gray, so it has been taken 0.8 or 0.6, 0.5. So on for the 0, so the pixel values and varies from 0 to 1. Okay, so this is the data that has been extracted. So there is a pre-processing work and all. So we'll be, if you have to do the PCA, you'll be having the data set. So these are pre-processing steps that generally person do. So this is a okay. So it has been done for this number. Like for example, this is done for 1. So similarly, it has been done for all the 60K data set, whatever they are having, on which we are just concluding, or we are using that PCA. So PCA generally, what PCA helps? PCA generally will help us. So okay, so we were having 28 cross 28 pixels. Okay, so 28 cross 28 pixels, right? So like for example, F1 to some sort of F28, and here again from F1 to F28. Okay, so 28 cross to 28. So each value, so you can see that each block can work as a features for us, right? Like for each features, there will be some values that can vary from 0 to 1, but each of the block will be having some value. So we'll be having now how many features? 28 into 28, right? So this should be around 786. So this is the number of features I'm having. Are you getting my point? How does that features number is set to 786 here? Are you able to hear me?
Yes,
Yes,
sir.
sir.
Yes.
Yes, we can hear you.
So are you getting my point? Like how did this features number is 786?
The total number
Yeah.
of cells is
The
Okay,
number
so
of cells.
okay, I'm just
Yeah, it's kind of matrix, sir. 28 by 28.
28 cross 28 is a matrix, and each block is having some value. Like for example, I told you here. So see, this has been converted into a matrix form. 1 was there. So wherever there's a dark black, it has been taken 1, the value of that block, right? Wherever there's a bit gray, but as in the value has been taken as 0.8, and lesser gray as 0.5, some sort of things. And wherever there's a 0, the block has been taken 0, right? So each of the value, each of the block can work as a features for us, right? For example, this is a one example. So similarly, I'm having 60K or 1 lakh of this type of training data set. Okay, so I'm having
So
this
each,
data. Yeah.
each and
This is one particular data set, right? For this image.
For this image, this is a one data set, you can say, and each of the block can work as a features for us. Like this data set, I'll convert that into a different matrix. Like for example, I'm having 78 plus 28. So now I can flatter that value. Like for example, I can do the row flattering or column flattering. That means I'll just take each of the value starting from here to here. I'll just write in one row. So that will go from 1 to 786 because I'm having 786 block, and each of the block will be having some sort of values, right?
Yes.
So this was for the first data set, right? So this was for the first image I'm having.
Okay, so it's like converting matrix values into a list.
Yeah, just I'm flattering the value. So I'm having now features 1 from features 1 786, right?
Yes.
Similarly, I can have some data set where here it was written 1. So so I told you I'm having 60K data set. 60K times it has been written with a handwritten, and that handwritten with some computer vision techniques and all, we have just converted that value into pixel, and pixel has been taken by us, like some sort of pre-processing and is done, and they have given me this value from 1 to 786 as a form of features. Like I'm having a 786 dimension of that. So whatever the data set I'm having now, so this till x1 to 60K x, okay, this I'm having all the data set. These are the training data set I'm having, and for each and every data set I'm having 786 pixel, or not pixel value, you can say the dimension I'm having 786 dimension, right?
Yes, sir.
Okay, so now what I have to do, yeah, so this can be a matrix. This data set can be a matrix of 60K cross 786. This is the row and this is the column. So column is generally represent the what you can say the dimension. Okay, so if I'm for example, I'm telling you, even I'm having the data set of 4 dimension, it's very difficult to visualize that, right? If I'm able to convert that 4 dimensional into 2 dimensional, then it's pretty simple to at least visualize and to see it also, right? So similarly, what we'll do here, we'll try to reduce the dimension from 786 to 2 dimension, so that I'll be able to visualize and I'll be able to know which sort of points is representing 1 from 0 to 9. Okay, so PCA can help us in that. PCA is generally a dimensional reduction technique where you'll be able to reduce the dimension from a very bigger number to a very small, so that you can have you can visualize those data set. Okay, and you can work also. Like for example, if you are giving some algorithm this data set with 60K cross 786 dimension, okay, it will take generally it doesn't take much time, but the time complexity of the algorithm will also decrease if I'm able to convert the 786 to a 2 dimension or 3 dimension. Okay, there will be some loss in the interpretability, but yeah, so that that will be losing some of the information, but will not lose much of the information, right? So we'll be able to convert that also we can fix. Like when you'll do that coding structure, you'll be able to fix that also, how much of the information you want to lose. Okay, like for example, I want to lose the information, so I want algorithm to work such that I'm able to grasp the 90% of the information, then also I'll be able to have a good accuracy, those sort of things. Okay, so I don't want to lose much of the information, right? That can be doable. So like in this blog, so that author has converted this 786 to a 2 dimension. Okay, so like for example, I told see, so there are other methods also. Just we'll go through the PCA method. So PCA, there are other methods like Disney and all that nowadays has become very famous, but PCA also works in a good way. So this I guess this blog is of like 2014 itself, so it's a 8 years old blog. So all this data set, now see, if we are able to convert this in a PCA form, see what happens. One second, guys. 771062. So see, this had been converted with the help of PCS. The algorithm analysis has not been shown. Just the final result here has been seen, like shown in this paper. So see, you can see that this data set generally represents one, right? So this bunch of data set is represent, like after converting a 786 to a two dimension, then also we are able to like see that the much of the information has not been lost. We are able to categorize, right? So see, this point generally represent 2, right? These are the point representing 2. So here it is 3. So these are the points representing 3, right? So these are the some, like if you'll go through that, you'll be able to, this is representing 6. If you'll see that 6 and somewhere the 0 is also somewhere seen as 6, right? This is 6, right? So the bunch is there, the 6 is showing 6. Here it is 2. Okay. So this is how generally the PCA is helping us to visualize or reduce the dimension from a very large dimension to a very low dimension. There are some other method, like you can see the optimization based dimensional reduction. Okay. So see this how, okay, these are different, like this we have not studied, but these are different algorithm to reduce the dimension. Okay. So this is how, see, this also is fine. Even with the TCA, this is a one Salmon's mapping. One very famous is this one. This is the one very famous. Yeah, this is the famous one. So this, see, Disney has how this algorithm is working. So this has categorized all of the data sets, right? So this is representing 0. This is representing 5. This is 1. So this is how it's working. Is also 5, 3, and all. So see, 786 we were not able to even think of how that will be, like how that will be seen, right? So now after converting that into 2D also, so we are not able to, we are not losing much of the information also, and we are able to visualize also. Whereas those data sets which are representing 8 or 7 or 5, and right. So if you want to convert that into 3D also, you can see that 3D, where is that? Okay. So this is in the 3D, like 786, that dimension has been converted into 3D. So here also you are able to see that. So these are the chunk who are representing, say, 8, and here 6, 5, and so yeah. So this was a basic simple example why generally we do that. Now we'll go through the basic maths and simple concept, how generally it works. Okay, till now it's fine, right?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay, so I'll start with there. So okay, so I'll just ask you in the last, like nobody's having any doubt in this definiteness, right?
No, sir. It's clear.
So that is fine. So somebody was asking regarding uh,
So has this note been uploaded in the supplementary content?
What? Can you repeat that?
The notes which you're sharing this PDF, it's been uploaded in the supplementary content, right?
Your voice is not audible. Like, wait, I'll just connect it with my AirPod.
Yeah,
What you told?
yeah, I wanted to know if this notes has been uploaded to supplementary content.
Okay, so you want this note to be okay. I'll just
Yes,
add.
I missed my last session.
Okay, I'll just add this.
Thank you.
Okay, thank you. Okay, so why PCA generally, right? So PCA mostly we are using this PCA for that visualization. Like I told you, like I shown you also one basic example of that MNIST dataset. Please go through that blog. You can read that. I guess you'll be able to understand that blog. Okay, only read the PCA part. There are other algorithms also discussed there. Okay, so you can just read the PCA part. So the PCA generally help us for the visualization process that I shown you also, that how that bigger dimension has came to the 2 dimension and we were able to visualize. And one is to help in the model training. Like if I'm having, like for example, we were having that we were having 60K data set of the training data set with that 786 pixels. Like if I'll try to use some basic algorithm. Okay, so that generally will be if I'm able to convert that into a 2 dimensional, that will help us in the time complexity also, and it will work in a better. If I'm having a huge number of dimensions, okay, the accuracy will be a better every time. Like if I'm increasing the number of dimensions every time, like the features every time, so it will help a bit in the accuracy. But yeah, so if you want to have a good algorithm, so that compensate with both the time complexity and the time complexity and the number of dimensions also, you can go and can reduce that. That will help you in the visualization purposes also. Okay. Okay. So the first method, like the first thing is why we are doing this. This is simply for visualization purposes and to reduce the dimensions, so that will help us in training for the training of the data, like training of the algorithm. Okay. The basic geometrical intuition behind the PCA is this, like how does it work? So this is a basic example. Okay, you can correlate this example with the PCA. Okay, how does it start working? Okay. So I'm having 2 features. Like for example, I'm having a data set. So please hear this carefully. You'll be able to understand this. So if I'm having 2 features, like for example, features F1 and F2. Okay, and feature F1 is I collected the data of the Indian peoples. Okay, so I just took the data of the blackness of the hair of the person. Like I'm just talking about the Indian peoples whose most probably the color of the hair is vary from dark gray to black. Okay, so I'm not considering that red or green, black and all. Okay, and just considering I took the data from like Indian population who's mostly the color of the hair is normally vary from dark gray to black, right? So you'll agree with me. So if I'm just converting, I'm just normalizing this dark gray and black to some number sort of things. Like if I'm taking black as a 1, so I'll just consider this dark gray as what, 0.8, right? 0.8 to 1. So this features I collected the data set from some like 1,000 people. Okay, and some 1,000 people, what I saw is the features one, that was the blackness of the hair of the person. Okay, so it was varying from 0.8 to maximum 1. So this was the feature. So this is the data set for all the 1,000 people. Okay, and now to the features 2. So I took the data set, I took the data from the people just to use some algorithm to calculate the weight of the person. So I took height and blackness of the hair as a features to collect the final label. So the label generally is to collect to know regarding the weight of the person. Okay, so I collected the blackness of the hair, so whose values was not varying much for the most of the people, whose values was from 0.8 to 1 every time. Okay, and the second features for me was the height of the person. So you'll agree with me that the height will vary from
I can say 45 kg to some 100 or 110 kg for the peoples in India, right? Like I'll just give you a brief idea regarding this, right? But the blackness of the hair will vary from 0.8 to 1. Okay, so and with that, this two features I'm taking to know regarding the weight of the person. Okay, so out of this, yeah.
Sir,
Your
are we
voice is
considering height or weight of the person? Sir,
no,
are we
no.
considering height or weight of the person?
No, I'm considering height of the person. Like I came to you, I just like I collected the data from you, like the height of yours and your hair color. That is the features for me, and I'll with those features I'm trying to get your weight. Are you getting the point? So my level is weight. So I'm trying to get the weight from your color of the hair and your height. Are you getting my point?
Sir, F2, I think it is weight because it is 45 kg, 100 kg.
What?
Oh, for F2,
okay,
I
okay.
consider.
Sorry. I'm telling height, but I'm considering. Okay. So this height, what would be the height? Like it will be from how much? 5 in that 5 feet to how much? That 7 or 6.5, right? So it will vary a
Yes, sir.
bit, right? On those basis, I'm considering and I'm planning to calculate the weight of the person. Okay. So you'll see that the spreadness of the data in the features one would be very small, right? Can you see that the blackness of the hair, if I'm collecting 1,000 data sets, most of the people will be having black hair, right? Will you like, are you agreeing with me?
Yes, sir.
Right? And the height may vary a lot. A lot means it will vary like within this range from 5 to 6.5 or whatever the height, like 4 to 7. So this will have a broader range or broader variance, right? The features too. So you'll agree with me if I need to calculate the weight. So that blackness of the hair might not help much, and the height will be the one features that will help us much, right? It can not like help in some of the data set, but mostly if person is having a high like tall, his weight will be a bit more, right? Because the weight of the bones and all will be there. So what I'm trying to say, if I'm having two pieces, so what I'm doing here, I'm not talking about the D dimension. I'm just talking about 2D. How will I convert that into a 1D? This is how this and this all this thing can be work on the D dimension where D can be a very bigger number. So D dimension can be a very, very big. So I'm just trying to convert this 2 dimension to 1 dimension. That will give you a brief idea how to convert that D dimension into a bit small. So D to a D dash, where D dash is smaller than D. Okay, this is what I'm trying to do. So I'm just trying to convert the 2D into a 1D. So what I'll do here, so I'll see that the spreadness of the blackness of the hair is very less. So this is the spreadness of. So I've just plotted this. I've just plotted a scatter plot, and I can see that the blackness of the hair is very less. The variance or the spreadness of the blackness of the value is varying from 0.8 to 1. So that's what I can assume that the spreadness of this features F1 is almost constant for all the people. So whenever I'm using some algorithm, what is happening? My weight is generally calculated with the help of the height only. Okay, because the spreadness of the height is very high. So if the person is having very less height, will be having a weight very less. That can be one assumption, right? So what we'll do, if I have to convert this data set only into a 1 dimension, what I'll do, I'll just keep this, I'll just remove this features 1, okay? And I'll just keep that F2. Like for example, here we are able to visualize 2 dimensions. Like so if assume that I'm not able to visualize the 2 dimensions, so why to keep this F1 feature? I'll just remove this F1 and I'll just with the help of only F2, I'll be able to predict the weight of the person, right? So what I'm doing here, wherever the spreadness of the data is very less, wherever the values, some features is having the same value for all the data sets, so that is not going to help us to predict the final result or the level of the result, right? So what I'm doing, I'm just removing the F1. So after removing the F1 also, maybe some of our information can get reduced. Like for example, 100% was the earlier information. So maybe 1% of the information gets reduced if I'm reducing some features which are having a spreadness very less, like for all the like data set, that feature is almost constant. So I can remove this one. So I can just work with F2 features. So what we are doing here, we are just converting the 2D into 1D. And how we are converting that? We are just removing those features wherever the spreadness is very less. So we are keeping those features only wherever the spreadness is high. Okay. So this is the one thing in the, so this is how we have converted this 2D into 1D. This is a very basic example. I'll just go with a bit complicated one. Okay.
Sir,
Yeah.
I have a question. So what do you mean by we will keep the feature where the spreadness is very high?
Yeah. See, so you'll agree with me if I need to predict the weight of some person, right? So that his height will play a very huge role, right?
Yes, sir. Yes, sir.
If I'm having only two features, I'm having your like the color of your hair and the height, right? So your weight mostly will be predicted with your height, right?
Yes, sir.
Not with the blackness of the hair. Why?
Yes.
Because blackness of the hair, whatever the data I have calculated, like for the 1,000 people I have calculated the data, and for all that I can see that all of the person is having mostly the color of the hair is from dark black to black, like dark gray to black, right? So that features is remaining constant. That means the spreadness of the variance, the spreadness of the data is very limited in that feature, like the blackness of the hair, right?
Yes. Yes. Sir.
Because that is varying from 0.8 to 0.1 only, or 0.9 to 0.1. If I'm able to convert that the color into some normalized value, so I can see that the features, F1 features is having very less spreadness, right? But the height is having a very large spreadness. So I'll remove the features which are having very less spreadness, because that is not helping us in the calculating the final result.
Okay. Yes, sir. Thank you.
Okay. So this is what we are doing, and these are the sum, like to reduce the dimensionality from 2D to 1D, we are just skipping F1. That F1 is the features one, that is the spread, that is the blackness of the hair. And by reducing F1, we are just losing less information. We are losing a very less information because this you can see that the blackness of the hair was not helping us to predict the value of the weight, right? So what we are doing, so this is the most important thing, we are just preserving the direction of the maximum spread. So what we have done here, we have just preserved the height. What is the height? This height is the direction in which the spreadness is very high, right? So this is the direction where the spreadness is very high. So we have kept the features height only where the spreadness is very high. So like for example, this is a bit complicated one, not complicated, a bit more complicated than the previous one. So now I'm having two features, and that features we can see this is the data set. This cross marks is the data set I'm having. So you can just forget this F1 dash and F2 dash here now. So you can just assume this is my data set. This is my data set I've calculated for some 50 people, and F1 is the first feature and F2 is the second feature. And those features are representing in this way. This cross at the data point, which has been represented in 2D. Okay, now I have to convert this 2D into 1D. Like I did here. So here it was very simple to convert that 2D into 1D. But now here, if I'm having data set like this, if I'm having data set like this, and this is the one features and this is the F2 features. So now here we can see that both, if you will see the how generally we calculate the spreadness. So if you just project the data set, you can see the projection is from here to here in the F1 direction, and the projection of this data set on F2, what you can say, the dimension or the features is from here to here. So for both the features, the spreadness of the data set is very high for F1 and F2 also, right? Then how will you convert this 2D into 1D? Can somebody say? How will you convert this 2D into 1D if I'm having the spreadness of the data set? In F1, you can see this F1 dimension or this F1 axis is very high from here to here, because this value, if it will project, it will come here, and this projection will come here. And in the F2 dimension also, or F2 axis also, the variability or the spreadness of the data is high. Then how will you convert this 2D into 1D? Can somebody tell me? This is how generally we work.
Can we take a function of F2 and F1?
Function of F2
and F1. I don't know.
So,
Can we take a line?
We can
in
treat
which
both
the
of them
projection
as
is
single function.
lost in between those
Yeah.
points. I mean, line running through
Line
the
of
point.
best fit, we can do that.
but one by one, can somebody like, what is the first
We
thing?
can use the line of best fit.
Sir, I am saying ki we can combine F1 and F2 in
Okay, how
some
will you
way.
do that? Okay, in some way you'll combine that. Okay, how will you combine that? Like, is there any method that you can think of now?
F2 minus F1? I don't know. Or
You can
F2
take
by
the
F1.
line passing through those points, I guess, on which EPC projection is very less. The
1 plus F2 by 2.
like you mentioned in the previous photo, like it will look like something like a new axis which is going through that, like the direction.
But like I was not able to hear you. Can somebody say like
So
what?
what I was suggesting was we can have I mean, like someone else has suggested a line passing through this point, like a best fit line or something,
Okay,
on
okay,
which
sorry.
the loss is very less.
Okay, yeah. So I can get one line, this one. Okay, and then
Yeah, and if you have to cover more, you can have another perpendicular to that,
okay,
or you can
I'll
just select this one. Everything going
okay.
through, I mean, distance of this from the origin of all the
So
points.
or origin,
Projection
or
of the
like
connector.
you told the distance should be minimum, or minimum you told the error should be minimum, loss should be minimum, right?
Yeah, yeah.
So okay, so you told me, okay, I'll take this direction. One in spite of F2 and F1, I'll just take this direction, right?
Yes.
Okay, so this is a good try. Like this is
I
a
mean, in
one
that,
of
the thing what I felt is the information has been saved because in the direction, the difference or variance is more in that direction.
yeah, correct. So yeah, super. So so this is the anybody else wants to try? Okay, so I'll just tell you. So whatever he has told is totally correct. So we can have some direction, not like for example, this was the data set we were having. So what I'll do, I'll just want that direction. So just focus on that word. So I just want that direction where the spreadness is very high. Okay, so in the first example, what I did, so I was having this as F1 and this was the F2. So this was a height where the spreadness was very high. So I just kept the height and I just forgot the F1 because the spreadness was very low. So in this example, because we can't remove F1 and F2 directly because the spreadness is high in both the, if we are projecting the data set, we can see that the spreadness is high. So what I'll do is I'll just take one direction, okay, one direction such that the spreadness is very high. Okay, so in this direction the spreadness is very high. How can you say that the spreadness is very high? If you will take this direction or this vector, you'll just, so you just took one vector v1 and take another vector that is perpendicular to u1. Okay, so this is the u2. So the two dimension I took. Okay, so how did we can do this with the rotation also? I just rotated the earlier axis. So now I'm having two dimension, or now I'm having two direction or two vectors. One vector where the spreadness is very high. So you can see that in this direction the spreadness is this much, right? So I've converted this F1, F2 into in such a way that now I'm having only this direction where the spreadness is very high, and in this direction the spreadness is very low. Are you getting my point? So if you project all the data set on this direction, you can see that the spreadness is from here to here. And if you project all this data set on this perpendicular vector that is perpendicular to u1, so you will see that the spreadness is very less. So again, we conclude after rotation, we came to the same example that we did in the F1, that we did in the earlier example, where we were having one feature as blackness of hair and other was the height. So you can conclude that U2 has been converted into F1, okay, because the spreadness of the data set is very less in U2. So you can remove this X2 and you can directly convert this 2D into 1D where the direction is this V1. And U1, you will see that in the end, why we are working on eigenvector and eigenvalues. So you'll see that whenever you are having some data set, okay, so some m cross n, some bigger, like we were having 60k cross 786. right? So what you will do is this is some A matrix. So you have read in the SPD, right? As A cross A transpose A, you have calculated, and then you will calculate the eigenvalue of that A transpose A, and that you will calculate the eigenvalues, and the eigenvalues that is very big, like the most bigger eigenvalues will correspond to that eigenvector where the direction is where the variance is very high. So that is what you need, right? So you need that eigenvector, or you need the eigenvector, you need a one direction where the spreadness is very high, and that is what you have got here. So you have just converted this F1, F2 to one direction where the variability or the spreadness of the data is very high, and the perpendicular one, like generally you got this eigenvectors. Whenever you calculate the eigenvector of the symmetric matrix, you get all the vectors which are very much orthogonal to each other, right? So here also you got u1 and u2, right? So you have got, because we were having only two features, so you got 2 cross 2, and then the eigenvalue, you got 2 eigenvalue, you got like you got eigenvalue as 10, and the other eigenvalue you got very less, 0.5. So what you will do, you will just keep the vector corresponding to the eigenvalue lambda 1. You will skip this eigenvector because this is not giving much information. How will you calculate the information? How much the information you are preserving? Generally, this is a one formula. There can be some other formula. Generally, you calculate this as a how much information you are able to preserve. So lambda 1 upon all the summation of the lambda. So lambda 1. So like for example, I'm having 786 data set, or I'm having 5-dimensional data set. And in that 5-dimensional, I'm having one lambda is very big, 100, and the other lambda is very small. Like all the other lambda is 1, 2, 3, 4, 5, 4. Like, so what I can convert this 5-dimensional into 1-dimensional without losing much of the information. How will you know that you're not losing that much of the information? So you can calculate this, the 100 plus 100 upon 100 plus 100 plus this, how much is this one? 10. So you are able to preserve this much of the information, like 10 upon 11, that is around how much percentage? Yeah, 90 more than, how much is that? 1000 upon 11. So you are able to preserve much of the information, right?
98.
So 90, yeah, 90, approx 90%.
98.
Right? So, okay, 98. Are you correct? 98, huh? Yeah, 98, correct. So you are able to preserve 98% of the information, and then also you are able to convert that 5D into 1D, right? So here you were not able to visualize anything. Now you are able to visualize also, and your much of the information are there, right? So now if you work on the if you like, for example, I'm having some 10,000 of the data set. So earlier I was having some matrix in the form of 10,000 cross 5. Now I'm having 10,000 cross 1 only. And then also I'm getting, if I use some algorithm to calculate the final answer, you'll see that the accuracy also doesn't got impacted very much, because we are not losing the information. When you would have read regarding the entropy and all, also in the electronics generally, we are taught regarding the entropy. So this is simply the example of the entropy only. So information generally is entropy only, right? So if you're not losing the information, if you're not losing here, after converting that from 5D into smaller, like 1 or 2D also, you're not able to lose the information, and you are able to get a good algorithm with a good accuracy. That is not much lesser than the earlier one. Okay. Every time if you are having a bigger dimension, you'll get a good accuracy only, because whenever you'll get you'll start increasing the dimension, somehow it will help you to get a bit more accuracy, or it will like work good. But if you are able to do that, if you are able to get those sort of accuracy with some lesser dimension, so you're able to get a optimum algorithm, right, to work on that. So this is what generally we do. So I'll just go through again this one part. So I think so you have got the point how generally this is working. So if I'm having two features, so we are just preserving those directions where the variance is very high, and we are just losing those dimensions where the variance is very low. And how are we calculating those? Those are how we are doing that. You have to see the lecture for that. How this thing getting converges to an end point where again you will be going to the eigenvector and eigenvalue. I told you what are the final value. I didn't told you how we are going. So I'll just tell you a brief about how we are going in that direction also. For more clarification, you can go to the lecture that we'll discuss on the Wednesday also. Okay. So this was the thing. So we were having F1 dash and F2 dash. One was the direction where the variance is very high, and this is the direction that is perpendicular to F1. Okay, we have dropped the F2 dash, and now we are having F1 dash, right? So if I'm able to project all those data sets on the F1 dash, right? I'm able to project all the data sets. That is how we are able to convert that 2D into 1D, right? So what we want, so we just want a direction F1 dash such the variance of all, if we are able to calculate the variance of all the data sets, so that is very huge. In this F1 dash direction is maximum, right? And F2 dash, if I'm having only 2D dimension, and that I need to convert that into 1D, so we'll just consider in those directions only the variance is maximum, or the spreadness of the data is very high. So we'll just skip the other one. Okay, so till now it's clear, right? So why we are doing this piece here? If you're having any doubt, you can ask. It's fine, right?
Yes, sir.
Okay. So okay, so you already know how, if I have to project this data set on this U1 direction, basically you can directly do this, like you can directly do the dot product also, or X1 transpose U1, that is also fine, or U1 transpose X1 upon on which direction you are doing. If you are doing in this direction, just have to square it. So this, consider this as a unit vector, like, so you just have to get the direction. Okay, so you can get the direct unit vector in that direction where the variance is very high. So that direction we have to get. Okay, so how will you get that? There are many methods to do that. There are like optimization, very different optimization techniques, like the gradient descent and all, that can be useful to know regarding the direction in which the variance is maximum for our data set. Okay, so this problem we can solve with some other algorithm, like gradient descent, or there are other like algorithm also that maybe you'll read in the next week, in the 8th week, I guess, or 9th week. Okay. So what we have to, what is the task? What we have to give to the that algorithm or the optimization technique? Okay. So what we have to generally solve here to get the, so what first we have to get the direction. Okay. In that direction, if you will calculate the projection of all those values, after projecting that value, so you got this vector. Okay, you have projected all the data sets, and now in this direction, you would, like, for example, you can't get directly, like, so the algorithm will take many of the vectors, right? So if this vector, he has got this direction, just projected all those values in this direction. Okay, so this is a U1, projected all the data set on this direction, on this vector. Okay, so now what is our task? We have to get U1 such that the variance is maximum. What is the variance? Like, for what variance? The projection of all those data set on this vector after projecting all those data set on the U1. So the projection of all the data set on U1 should be maximum. Okay. What is the constant? The constant is that it should be a unit vector. So this is how, the constant is this one. So U1 transpose U1 should be 1. So that is the unit vector. Okay. So this is this. And how will you calculate the variance? So you can calculate the variance. The simple formula for the variance is what? So the difference of what? Whatever the data set you are getting now, subtraction of that earlier data set, okay, and the squaring, and then divided with the end value. Okay. So can you please explain the figure 2? Which is the figure 2? So Harshit, are you talking about this figure? Or which one you are talking about? Okay, so if you'll reply, I'll just go through that. Okay, so this is our task. We have to get the U1, or the direction of the vector in which the projection or the variance of the projection of all the data set is maximum. So this is our problem. This is our task that we have to solve. So we have to solve this, and the constant, the given thing is U1 transpose of U1 is 1. Okay, so this is the thing that you have to solve, and you have to get the U1. Okay, the direction in which the variance is maximum. Okay, this is a constant. So this. Okay. So this is our problem that, so this is the one approach to calculate the PCA. This is the variance approach. Okay, this is a variance approach to solve and to get the U1. There is another approach also. That approach is that one guy told regarding the, we can minimize the reconstruction error. That also can work, right? So if I'm able to get that direction where the error, the reconstruction error is very less, that direction can also work, right? Like for this is the minimum reconstruction error, right? For example, this is the direction that we got. This is our data set. Okay, so this was the earlier data set xi. That this is the xi and this is the xi dash. This is the xi dash, that is the projected value, right? So now we have to calculate the d. D is the minimize, like this is the reconstruction error, right? For example, I chose this direction, and now this direction, how much distance is the earlier data set from this direction? So we'll calculate the d1 like di, okay, for all the error, for all the not error, for all the data set, and that we have to minimize. If I'm able to minimize that, and in minimizing that, if I'm able to get that direction, so that also can work as our best direction. Okay, so in spite of that f1 f2, I can work on that u1. Okay, that will get after reducing the reconstruction error. So both, if you will go through the proof of the reconstruction error or the variance, either you are minimizing the reconstruction error or you are maximizing the variance, you will just see that you are concluding to the same point where that direction is the eigenvector corresponding to the maximum eigenvalue. Okay, so from both, this is both the way to just reach the same fixed point. That is the direction, that is the direction of the vector corresponding to the maximum eigenvalue. So from, if you are able to solve this also with some optimization problem or with some optimization technique, you will see that after solving, after minimizing this equation with this constant, this is the constant that this is a unit vector. If you solve this, you will see that u1 from here also, or you are solving with the help of variance approach, you will see that both the u1 are concluding to the same thing, that is the eigenvector corresponding to the maximum eigenvalue of that A transpose A. Okay. So this is the things to remember, that you will see after going through the lecture, you will be able to know how we are doing that. So I just told you why PCA and what are the end result of the PCA. I didn't told you how we are doing that. The basic approach I told you, the basic approach of variance or maximize the variance with help of some optimization technique, or with the help of minimizing the reconstruction error. Both will help you to go to the end point, that is you need to get the direction where the variance is maximum or the error, reconstruction error is minimum. If you go through now, maybe you'll able to get the point in the lecture. Okay, so this was the brief idea regarding PCA this whole 6th week. So we have discussed in this, I guess, half an hour. Now if we'll go through the lectures, we'll be able to get the point, I guess. Yeah, you'll get the eigenvalues as the number of original dimension. Like for example, if the dimension was like, so that depends, right? If you are able to convert that rectangular matrices into like if the matrices was 6 cross 3, so just calculate the transpose into transpose, like A transpose into A. So you'll be having 3 cross 3. So you'll get 3 eigenvalues and other eigenvalues will be 0, right? So that you have already read in the SPD. So till now, if you're having any issue, you can ask, or I'll tell you some more blocks from where you can read the ML thing. Yeah.
Sir, yeah, you told we'll be selecting the singular values with the maximum, like the highest singular value, right? Which saves the most amount of information. So basically, we'll be selecting the, let's say we're selecting sigma 1 and sigma 2. Then we'll be selecting the first 2 vectors as well, right? Or for example,
no, if you are okay. So if you are selecting sigma 1 and sigma, okay, lambda 1, that also will correspond to the maximum lambda value only. So if you are having lambda, this lambda, so generally we try to write that eigenvector in that form. Like for example, I'm having lambda 1 greater than lambda 2. I'm having 10 dimensions. So I'll just write in this way. And corresponding to the maximum, I'll just try to write this vector v1. So that the vector corresponding to the maximum lambda value will represent this v1, right? So this would be the direction with the maximum variance.
So we are selecting V1. Why I asked this, like usually we have the two component, right? So when we do A transpose A, we get this lambda value, then we take singular, and then we select, for example, any matrix A can be written in the form of Q1, that sigma values, and Q2, right? Q2 transpose.
Yeah. Mm-hmm.
So we'll be taking vectors from Q1, right? Or we'll be taking from Q2 transpose. I'm talking in terms of SVD, so either it works.
Yeah, either it will work, right? Because see, the second one came from the first one itself. Because the second one, how did the second one came? The second one has came from like this, sigma 1, right?
Yeah.
So both.
Got it. Yeah. Thank you.
So to find sigma, we take A transpose into A or A into A transpose.
Anything will work. Like both, generally A transpose A or A transpose, both are having the same eigenvalue. But if you are having, for example, if you are having A as 5 cross 4, so one thing you will get 5 cross 5, and one we will get 4 cross 4, right?
Yes.
But in the 4, whatever the eigenvalue you will get, the same eigenvalue you will get here. One eigenvalue will be 0 here.
It's just that if you're doing it for the input, then it's better to take Q1, right? Because the dimensions will match.
Yeah.
Thank you.
Yeah. So anything else? Like, okay. So I'll just tell you one more thing. Okay. So that information.
Another small query.
Yeah.
Can we go back?
Can you go on solving a problem on SVD, like complete steps? That would be helpful, I guess.
Okay. I'll just
Anything from the practice assignment?
Okay, I have from one slide. I just got it from some university. I don't know where. Handout is there. I'll just go through that. There will be some example, or else we'll just go through some practice assignment. Okay. So this I got from some, I don't know where, this I searching on the Google and I got this. Okay. So what do you want? This C, this U or V both generally is like one is the orthogonal matrix with A transpose and A, other is a. So example you want, right? So see this, if A is a M cross N matrix, then A transpose have same non-zero eigenvalue. And if one matrix is a bigger one, so the rest of the eigenvalue will be 0. So this is an example. So I'll just go through this example. Is that fine?
Yes, sir.
So this is the A, right? So this A that is 2 cross 3, fine. So A transpose is what? 2 cross 2, and A transpose A is 3 cross 3, right? That you can calculate. So what generally you have to calculate in SBD? We have to get the symmetric, like the A transpose A or A trans, so both A transpose A and A transpose. Okay. And now what you will do is you have to calculate the eigenvalue and eigenvector corresponding to those values, right? So you got this, you have calculated the eigenvalue for A transpose. Because why he has calculated? Because why didn't he calculate it for 3 cross 3? Because it would become a hectic one. So just he calculated for 2 cross 2. So whatever the eigenvalue you'll get, the same you'll get for this, and one more 0 is that, right? So he has got 16 and 6 as the eigenvalue 9. Okay, so now what is the sigma is basically root of 16 and root of 6, right? So see, so for A transpose, what he got, the lambda 1 has 16 and lambda 2 has 6. But for A transpose A, he got the same lambda 16 and 6 and one more lambda, because here it was 3 dimensions, so you got one one eigenvalue is 0, right? So the singular value generally is the square root of the A transpose A. Like whatever the eigenvalues you are getting, just do the square root, you'll get the singular value of that matrix. Okay, so sigma 1, sigma 2 you already got. Now what you have to do? You have to get the eigenvector, right? So you have U and V, right? So one you can assume A transpose as U and A transpose as V. So now what you have to do? You already got the eigenvalues corresponding to the A transpose A or A transpose vice versa. So what you got, now you have to conclude, you have to know regarding the eigenvector. So if you are able to calculate the eigenvector from that eigenvalue, right? So you have calculated that. So corresponding to the 16, you got one eigenvalue. Corresponding to the 6, you got one eigenvector you got, and one eigenvector you got corresponding to that. And then corresponding to lambda 3 also, you got some, because you will be having 3 eigen corresponding to that A transpose A, or according to the matrices you are getting. Like if you are getting 1 2 cross 2 and 1 3 cross 3, so if he is able to calculate the 3 cross 3, he'll get 3 eigenvalues, right? So 3 eigenvalues. So from 3, so he got 3 eigenvalues. So what he did, he just normalized all the 3 and then wrote in the form of matrix. So now he got V. So V is already there. Sigma, you already know, sigma is the same, like sigma will be the M cross N matrices with the diagonal element will be the non-zero square root of that square root of the eigenvalue. So sigma also you got. So how will you calculate the U? So U generally you calculate, you can just multiply the whatever the matrices you have got to that of A and then divide it with the sigma. This is how generally you calculate, right? So here what you did, now you have to calculate the U here. So here he has calculated. So here A, so you just you have to, if you have to calculate U1, what you will do, will this A you are having, A matrix you are having, V1 you already have, now sigma 1 you already have, and U1 you have to calculate, just divide it with the sigma 1, you will get the U1, and then normalize that to get the final U, capital U. V you already calculated, sigma you already calculated, U also you calculated. Okay.
Sir, I didn't get it. How did they calculate U?
Okay. 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 So this was the question for yesterday. Okay, so this was A transpose A you have calculated. Now you have calculated the eigenvalue. Now you have calculated the eigenvector for A transpose A. First you have calculated for A transpose A. So after calculating A transpose A, now you are having Q2, like Q2 or Q1, whatever you want to write, like Q or B. So one thing you have calculated, Q2 you have calculated. This can be written how, like Q1 sigma Q2 transpose. So Q2 you have got now. So whatever this column will help us to know the first column of the Q1 also, right? How will you calculate this multiplied with the A vector? So how will you calculate the Q1? So Q1 can be calculated. So Y1. So Y1 is the first column of that Q1. So how will you do that? A multiplied with the X1. So you have got X1. X1 is what? The first column of the Q2 matrix. Q2 matrix, how did you got the Q2 matrix? Q2 matrix is the eigenvector, normalized eigenvector. So we have multiplied now normalized eigenvector with A matrix and then divided with the sigma 1. Sigma 1 is the square root of the eigenvalues. And then you got this Q1 and then you have to normalize that. Okay, so similarly, you'll get the second column of the Q1. Second column of the Q1, you'll be getting help from the second column of the Q2 multiplied with that A matrices divide by that sigma 2. Here sigma 2 is 0. So what he did, I don't know. So like I just told you the procedure. Like for all the cases, you'll be having sigma 2 as 0. So every time you'll be having some eigenvalues, right? So you can just divide it by that fixed value and then you can get the second column, right? Have you got the point? Like maybe some chunk of thing you have got.
Yes, sir. And now what are they doing in this case, as they have got sigma 2 equals to 0? So what are they doing here?
Okay, so if you are getting 0 as other, so both will be orthogonal. I guess the same method he has used. Something is like Y1. Okay, so Y2 is 0 here because the sigma 2 is 0. So Y2 would be perpendicular to that one. So he would have just, like if I'm having X1 and X2 here. Okay, so this X1 next to. So you can take this X2 as X1 and this as X2 with some one of the thing as a minus, so that the product will become 0, right? This can be a one eigenvector. Have you got the point? See, y1 is what? Y1 and y2, if you see the dot product of both, it will be 0, right? Because the orthogonal also, and the second part, the eigenvalue is 0. So see. So here, what was there? So y1 and y2 was perpendicular. So the dot product would be 0 for that. So y1 was having some value x1 and x2. So for y2, what he took x2 and x1. So you can take this also, or x2 minus x1. So that the product, when you will calculate the product of both the things, you'll get 0 as a final answer. Like you will multiply, like for example, this transpose x1 multiply with x2, x1, x2, and then 1 would be the subtraction. So again you will do that x2, x1, x2. So you'll get 0. This is what he has done, because both are perpendicular, y1 and y2. So what he did, he just took the same element in the reverse order and gave the 1 minus sign to the one of the two, so that when you will calculate the dot product, it will become 0. In this case he has done, but not in every case you'll get this type of thing. Okay, so the Q1 was calculated earlier, Q2 has been calculated, and this is what he has done.
If there are like 3 vectors or something, I mean 3 singular values, even in that case we'll be doing the same. Is it like let's say sigma 1, sigma 2, we have some positive number, non-zero number. If sigma 3 is 0, then we'll just take a vector which is perpendicular to both of them. We'll do something like that.
Yeah, so both that vector will be perpendicular. Complex, right? Yeah, then it will become a bit complex. Right. If you're having some example, then we'll go through that.
A into A transpose and find the third column with respect to that. Can we do with it match?
What, A into A transpose?
For example, let's say anything can be decomposed into 3 parts. Right? First is Q1 and so that singular value matrix, and Q2. So Q2 transpose will find in the same way, like A transpose into A will do, and we'll get a sigma value and eigenvector. But Q1, can we do A into A transpose and find it separately? Will it match? Was I clear?
Okay, so what you told, if we are having,
let's say any matrix A can be written in form of Q1. Yeah. Q2 transpose. Q2 we'll find it in the method like A transpose into A is equals to. We'll find it. Yeah, this method we'll find out Q2.
Yeah, so this method you can calculate the eigenvalues and then corresponding to that eigenvector, right?
Yeah, and the Q1 can we find directly by A transpose?
A transpose.
Yeah, that will also will get an eigenvalues and eigenvectors. Okay, I'm just curious, will it match? Because there can be different eigenvectors for same, different linear combination of eigenvectors.
So you'll get from here also you'll get the same eigenvalues, right?
Yeah.
So you'll get the same thing again.
No, here eigenvalue same, but I'm talking about Q1, sir. Eigenvectors for Q1.
No, see.
Can I find in this way?
So this Q1 is A transpose A transpose, right?
Yeah, I know eigenvalues will be same, but eigenvectors will be different, right, for both of them. I'm just considering a scenario where, let's say there is one zero value. In that case, it will get very complex, right, to find an eigenvector in the formula that A, B, 3 by sigma 3. In that case, can I do this?
Eigenvalues would be same, but eigenvector can be different for those cases.
Can we do in this method?
I'm also not sure about that. I need to see that. Maybe we can check on the Google or somewhere.
Because I'm not sure how can we calculate that eigenvector when sigma 3 is 0. Like sigma? In that case, there were only 2 vectors. He found them perpendicular to one of them. Let's say there are 3 singular values.
Okay.
in which one is 0. In that case, we have to find the vector which is perpendicular to both. Then the calculation will get a bit complex, right?
Okay. So see, in this case, okay. So in this case, what he did. Okay. So what he did here, see, you told I'm having one vector, one matrix 2 cross 2 and one matrix 3 cross 3, right?
Yeah.
So if I'm having, if you, so what you can do is, you can calculate the eigenvector corresponding to the 3 vectors, 3 eigenvalues first, corresponding to 3 cross 3, right?
Okay. Yeah.
So what he did here, he just calculated the corresponding to 16, corresponding to 6, and corresponding to 0, right?
Okay, got it. So it becomes easier for the next one to
Yeah.
find the 0 vector. Okay. Just we have to find the perpendicular of the existing one.
So this is how we has calculated. So first we calculate for the bigger one and then for the smaller one, so that it becomes easier.
Okay, thank you.
So, okay. So anything about this, whatever we have discussed this piece here? And now you can go through the lecture, I guess, and maybe it will help you to grasp now. If somebody has seen that, it's fine. We'll discuss the proofs in the next lecture, but the proof is not going to help you much. So this is how the basic maths behind the PC. And if you're having any doubt regarding this also, well, earlier it was in the 6th week. Now it has been moved to, now the PC has been moved to 7th week. This was earlier in the 6th week. So one question earlier, somebody asked me if I'm having this, if I'm able to, second derivative is able to, is if I'm having some term with xy also, right? If you are having some term with only x and y, you can directly say. But if you are having some term with xy also, so calculate the second derivative for each of the term and then calculate the determinant. And if the determinant is positive, you can directly say. If that is negative, that's a saddle, and if 0, then you need to go for further more test. Okay.
So can you solve one of those problems in this in the activities on the constitutive definiteness, in which they had mentioned which of the following is the A, B, C, D, that matrix has been written, and they asked which is the correct one.
Okay. So
in the activity questions, about the question, but I think it's in graded. Sorry, not graded. The practice questions. Practice assignments.
this one you are asking?
No, so not this. They give a matrix in the options. Yeah, one of them.
Okay.
Yeah.
So this you can, okay. So this you can do with the help of comparison. Like you can just write ABC and then, because it's symmetric, you can just write B here and then compare, and then you can get. Like earlier, I was thinking that Hessian matrix generally will help us, but Hessian matrix is generally the second order derivative of any equation, right? So that is not going to give you the same matrix. That will help you to know the nature of the eigenvalues and to know the nature of the matrix. Okay, but that the Hessian matrix is not going to help you to give you the exact matrix. That will help you to know the nature, but not the exact content of the matrix.
But Hessian matrix will give us this, like it will be valid, right? Let's say I replace this 3 cross 3 with whatever Hessian matrix I get. That will give us a valid solution, right? XYZ into that matrix, XYZ transpose matrix and XYZ. It will actually give a solution, right?
It will give you the solution that will help you to know the nature. It will not give you this exact same matrix. I'll calculate
solution. Yeah. That will also be valid one, right?
Yeah, that will valid if you have been asked to know regarding the nature of the matrices. Okay, so how does that the matrix will behave, that Hessian matrix can give you, but that Hessian matrix is not going to give you the exact content or element of the matrix.
Yeah, the elements were different in that.
But the nature can be calculated with the help of, because Hessian matrix is simply the second derivative of any equation, and second derivative of the equation can help you to know regarding the nature of the eigenvalues, because you can get the idea regarding the definiteness of the matrix, so you can say about the eigenvalues also. Okay.
So in that case, the above one, it was just like trial and error. We had to calculate all of
You
them
have to
and
go,
cross-check.
you have to just write some A, B, C, D and then compare the value, or you can directly go to the trial and hit and trial and will be able to calculate.
Okay, so it's not a Hessian matrix method.
It's not Hessian. I was also confused because I didn't solve any problem. So I was pretty sure that is the Hessian matrix. But after calculation, I came to know this is not the Hessian matrix. Hessian matrix simply Hessian matrix generally gives us the second derivative, the second partial derivative of anything.
But again, in the Hessian matrix, if we put that XYZ transpose that Hessian matrix into XYZ, it'll actually give us back the equation, right?
I don't think so. It will give you. See, I'll just calculate that.
So then how to solve such questions? How to represent? Because for 2 cross 2 we can do that, but 3 cross
even
3.
for 2 cross 2, you can see that even for 2 cross 2, if you are calculating, the Hessian matrix generally doesn't come same as matrix, right? Like for example,
sir, I'm not talking about Hessian matrix. We can represent that matrix as A, B, B, C. But how to represent in 3 cross 3?
I guess till now, whatever I know, I guess the only method is to compare the value. Like you can just, like if I'm having 2 cross 2, you can write this A, B, B, C, and then compare the values with A, B. Like this is X, Y, multiply this, and whatever the equation you are having. If you want to know the exact element of the matrix, then you can compare with this equation. Like you can just multiply this equation, and then whatever the value you'll be having, like example, you are having 2a x square, and here you are having 2x square. Then you can assume a is equal to 1. So this way is a one method that I know till now. Other method, I'm not sure. Maybe whatever, like if you can go through some Google document and all. I'll also try to get, but till now I didn't got how to get the direct exact matrix. Okay, this is the only method I saw to compare and get.
2 cross 2, it's fine, sir. Like you told, we can just compare that 2B and A and C, and we can get it. But when it is 3 cross 3, getting that exact value, it's like you have to do all the matrices.
It's difficult, really difficult. If you have the option, okay, you can go. But if you don't have the option, it's a painful job to do that. Like I can show you the Hessian. Like Hessian matrix doesn't give the exact element, that because I tried that.
Almost won't it give a solution? Then I thought it will give.
No, it will not. It will give you all the basic idea regarding the matrix, but it will not give you the exact element of the matrix. Like for example, see, I'll just give you the first itself, the first row, first column data, whatever I'm having.
I think the common terms can be taken out, right, from the Hessian matrix.
See, this is x square. This is the first term what we do. We generally do the double differentiation of the function with respect to x. If I'm doing the double differentiation, we'll get 2 here. Out of the 4 options, 2 is not there. So that is for sure Hessian matrix that is not going to give me the exact value of the exact element, right? Are you getting my point?
Yeah, but what I feel is like if we solve eventually in Hessian matrix, it will actually give this equation. Let's say we take this.
It will give you, see, if I'm having some equation, like for example, if I'm having some e to the power xy sine y, okay, if you have been asked to calculate the Hessian matrix, you can do that. Like you can directly x, y, and then z. If I'm having z also here, so z, and then you can do the part. Like it's simply like covariance matrix or the variance of the matrix of the second derivative, right? So you have to differentiate it with respect to x, and then x, y, x, z, y, z. Similarly, you have to do for all the 3 cross 3 matrices.
It won't give the exact that matrix. That's what
it won't give, like you can try, and if you are getting, you can help me out also. But
I think it gives. That's what I felt on that matrix. It is given that question. Like, but
okay,
you can just try out that question.
Okay, so can we try for this matrix?
Yeah.
Okay, so I'll try. See, x square. Tell me the x square minus z square plus 2yz plus xz, right? Okay, so I need to calculate the Hessian matrix. So what I'll do, I'll just differentiate with respect to x. So here I have to differentiate with respect to x twice. So if I'll do that, we'll get 2 here, right? 2x, and then I'll differentiate, we'll get 2. Now here I have to differentiate with respect to x. So 2x plus z, and then respect to y. So I'll get here 0. Again, I have to differentiate with respect to x and then respect to z. So I'll get 1 here, right? Here I have to differentiate with respect to x and then with respect to y. So I'll get 0. Here with respect to y twice, so I'll get 0. Y and then x, y and then z, so I'll get 2 here. If I have to differentiate with respect to here z and then x, so zx is there in,
I guess, in that question.
where?
So 2yz and 2xz, I guess. The fxyz equation.
Which equation?
This
No,
equation.
sir, the original problem has 2x.
Okay.
Yeah.
Okay. So this 2x, 2z. So if I have to differentiate with respect to x and y, so I'll get 2 here, right? Now if I have to differentiate with respect to z and then x, so again I will get 2 here. Here if I have to differentiate y and then z, so yz is also 2, like it's symmetrical also, and zz is minus 2. So this is the matrix we are getting.
Yeah.
2, 0, 2, 0, 0, 2, 2, 2, minus 2. This is the matrix I'm getting.
So we can take out 2 common or something.
Okay, I'll take out the 1 common, 1, 0, 1, 0, 0, 1, 1, 1, minus 1. Is there any matrix that is representing this one? I don't think
not
so.
Exactly.
Yeah.
Not same.
So not exactly, right? So this is what I tried, and I thought earlier I was assuming that Hessian matrix generally gives, but then I went through that some lectures of the Hessian matrix, and I came to know this is not the exact element like we are able to get from the Hessian matrix. So you can do only method that is left that I know. There can be other methods for sure, but I know is the method to compare the value and to get the value, or to do with the hit and trial if you are having options. Any other like questions or any other thing? So if you don't have anything, like because we have expected this session to be like less than 1 or 1.5 hours.
So I think if you take out the 2 and if you multiply that, we'll get this equation back.
Okay, so I'll take out the 2 and then I'll multiply with.
Just use the inside one 1 0 1 0 1 0 1 1. Multiply that same xyz transpose into this matrix into xyz. You get that equation.
Okay, so I'll just multiply. Okay, I'll just multiply this. So I'll multiply this with
xyz and xyz.
Okay, so xyz and xyz. So why so we have to remove this 2. Why we are removing this 2?
It was common, right? I just kept it out.
This.
I mean, I got a solution this way, so I was just. I think so. I just did a quick calculation. I may be wrong, but.
Okay. So yeah, so there can be some like wait, maybe something would be there like to divide the Hessian matrix with some hits. Okay, so what is the determinant value? 1, 1, 0 plus 1. Okay, it's a 0 only. So the determinant is also 1 for this Hessian matrix. So you told to multiply this. So I'll just multiply this.
X plus Z.
There is one simple formula I have seen in the discourse forum. Can I explain it?
What?
I have seen one simple formula in discourse.
No, okay, that is not the formula. That is a simple like you can also do like I told you. You can just write A, B, C, and in the symmetrical form, and then elaborate this with just multiply X, Y, Z, multiply that X, Y, Z, and then compare with the A, B, C value. You'll get the matrix, right? So that is the comparison method. That is the one method, but we are trying for something else.
Okay.
So So this method is also fine. Like one time only you have to do if you are having to do that A cross like ABC, like take the matrix in the symmetrical form. Okay, so I'll try to do this, right? So this is what? X plus G. This is 1 cross 3 and multiply with 3 cross 3. So I'll be having 1 cross 3. So X plus Z, and then I'm having Z, and then I'm having X plus Y minus Z. And that I have to multiply with X, Y, G, right?
Yeah.
By 3, this is 3 cross 1, this is 1 cross 3. Okay, so X square plus ZX plus ZY plus XZ plus YZ minus Z square. So I guess we are getting, oh, okay, we got the same thing, right? X square minus Z square.
Yeah, same.
Okay, so only, okay, yeah, so we got the same thing. But
I just kept the 2 out. I don't know why. Just
yeah, that 2, that is the only confusion I was having. So when I concluded, so for every matrix is what was happening, but like I was doing for the 2 cross 2 also, so some constant was coming out. So I was not sure why is it happening, and then I thought this is not the correct. Like I can get the anything about the matrix with the Hessian matrix, but I don't know why this constant, some constant is coming. So that we need to check. What is that constant?
And another query was like, if there is that 3 cross 3 matrix, do we have any, for example, we wrote A, B, B, C, there is any matrix like that which we can write right away?
Okay, which matrix? That symmetrical matrix?
Yeah, for A, B, B, C, that's what we usually write. So for the
this A, B, C, you can write D, E, right? And if you are able to write, this would be B, right? This would be C, and this you can write FF.
But if you see those options in that question, they were not like this, isn't it? They were not symmetric, I guess.
Which one?
In that activity, whatever the problem which you referred, the solutions were not symmetric.
Okay, it's not symmetric also. Okay, so whoever has made this question had just, I guess, made the, according to the option, he just created this option, this question, I guess.
Okay.
Yeah, so I guess there is some error in this question because you have to get some symmetrical matrix. So you can get any other matrices. Yeah, you can get some other matrices also, that is fine, but you can't use that matrix. Like you can't do much thing regarding the matrix that is not symmetric. So you can get some other, like here you can get the matrix. So whatever we have got, that was symmetric. Yeah. So whatever we have got was symmetric because we have calculated from the Hessian matrix. Because Hessian matrix generally gives you the symmetric matrix only.
Okay.
Because there we are calculating covariance and variance. So again,
in that question, I think there were a couple of them. They were all, I guess, in the similar state. Like they were not symmetric at all. So I guess.
Yeah. So this question has been just prepared according to the option.
Okay.
Yeah.
So there was nothing specific. Formula
But I guess from the Hessian, you can, there would be something else. I need to go through that. But most of the lectures, I like the books I read, the Hessian matrix, that there is not clearly written that you'll get the matrix from. You'll get the second derivative matrix that was written, but I don't know how is that second derivative matrix similar to that matrix, exact element of the matrix. Because here we are getting the matrix, but we are getting the in the 2 multiplied, the scalar form, right?
Yeah.
Yeah, so that I need to check. So I'll check, and then maybe, so you can also see that, like most of you can go through that Hessian matrix again, because those things are not been taught here. So those are like extra sort of things, but yeah, it's fine. Like Hessian matrix will be taught, I guess, in the 8th or 9th week, where you'll be knowing regarding the matrix. Like if you're having some matrices, with the help of matrix, how will you conclude that whether this the function or whether the equation is the convex or the concave. So those sort of things the Hessian matrix will help you to know. Okay, so maybe in the next upcoming lecture, you'll be going through that.
Thank you.
Okay, yeah, thank you. Thanks a lot. Like I was also like, I need to check again that regarding how does that scalar things will go and how will we conclude that. So anything else from anyone? Because I'll close the session. I need to go, and that your quiz marks, we have to sign off that today. Sign off the marks, quiz marks today itself. So that
can you upload that?
So yeah.
Week 6 thing in supplementary.
Okay, that notes I'll definitely upload this. And one more thing, some lectures will be uploaded that must watch. So that Professor Arun Rajkumar's video is there. That is of 2 hours. That happened if you have like, does any of you have attended that paradox workshop that he took? He took on the eigenvalues, eigenvector only. Okay, so that is very important. You should watch this. If you're not able to grasp if you're not, some of the people don't like the style of teaching of some like professor. Okay, so you can just go through this lecture also. Maybe it will help you to grasp more regarding the PC and eigenvalue, eigenvector. Okay, so this lecture will be uploaded in like 1 to 2 days. Till that time, if you want, I can upload in the Google Drive and then can upload on the Discord, or so that link I can give it on the Discord. Okay, but it will be uploaded by this weekend, I guess, Wednesday or Thursday. Till that time, if you want, I can just upload that on the some of my G Drive and then give you the link of that on the Discord itself. Yeah.
Sir, where will this be uploaded exactly? In the YouTube page or somewhere else?
No, it will be uploaded here itself in the supplementary content, or it would be written like extra content in the week 7 itself. It will be uploaded, but it's not uploaded yet because this video went for that what you can say editing and all. So then after it will be uploaded, this Wednesday or Thursday it will be uploaded. Okay.
Oh, okay. So uploading here, you're only referring to Professor Rajkumar's talk and not in general the other workshops.
No. Only the Professor Rajkumar I'll be uploading because that is relevant to your topics, right?
Yeah,
So,
yeah. Okay.
Yeah, there are other also, but I don't know how that will help you. But this will help you for sure. That's why I told them to do that editing and then upload.
All right, so got it. Thank you.
Okay, thank you.
Sir,
So,
regarding the question in the reflection quiz, the 2 by 4, which seems to be the intersection of 2 lines, no, sir? How the 2 by 4 later is being interpreted as a scaling of the 2 lines. How it has been interpreted as a scaling is what I didn't understand. Initially, it's referred to as the intersection of 2 lines. Suddenly, it's been interpreted as a scaling, as one line is twice, and the other one vector is becoming twice, and other vector is 4 times like that.
Okay, so I didn't saw that reflection. That is
okay. You may please answer. Put your answer in that discourse, so that we'll get a good idea, like how that intersection point turns into a scaling. That's what right now.
Okay, so I'll try to that by maybe tonight. Okay.
Not necessarily immediately, sir. Anytime, like within a few days.
Or else if I'll not post, I'll forward. You can mail me also. I'll just go through that because I have not seen that. What is that question?
Sure.
Okay. Okay. So thank you. Thanks a lot. So if you are having anything, you can ask. Otherwise, we'll close and I'll just go for some that cues, marks, sign off, and then because again we'll meet on the Thursday. Wednesday after you'll go through the lecture. So till now you have not gone through the lecture. After that, like maybe today, tomorrow, you have time, 3 days, you can go through that. Wednesday we'll meet. And if you're having any doubt regarding lectures, you can ask me on that day. Is it fine for everyone?
Yes, sir.
Oh, okay. So I'll just stop the sharing portion. So.
Thank you, sir.
Oh, okay. Thank you. So just close this session.